Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video we're going to be looking at Kp and its use for working out the equilibrium constant for gases. So when we're talking about the equilibrium constant K, we are merely thinking about the ratio of the products C and D to the reactants A and B. Now it's the subscript involved that designates what type of units this takes hold. So if it's Kc, C stands for concentration, so it's when you are working out the equilibrium constant through the use of concentrations. So you're looking for the square brackets in your expression, and the units are always going to be based on moles per decimeter cubed. Now this can be used for any chemical species that are aqueous, liquid or gas. You have to be given a volume in order to express the moles of each of these as a concentration in moles per decimeter cube. And a real focus, which will be really important in a second when we discuss Kp, is that if you're dealing with gases and being asked to work out a Kc, then you won't be given pressure if you're going down this route. On the other hand, Kp, the P stands for pressure, so this can only be used with gases, and in order to go down the Kp route, you need to be given the total pressure of the system, so the reactants and products together. And this is designated with capital P and a T for total, and in this case, you're dealing with the partial pressures, not the concentrations, of each of the reactants and the products. Partial pressures is designated from a lowercase p, sometimes it's italicized. So you can see here the expression is the products over the reactants, just like Kc, but you put a p in front. You don't use square brackets, it's these curved brackets. The units of these curved brackets depend on what the units of pressure you are using. So this can be either atmospheres, or it can be in pascals or kilopascals. The choice of units for each of these brackets will be dictated by what units the total pressure is given in. So just check that you are matching those across. Now, the partial pressure of each individual species, so for example C here, is how much pressure that particular component C contributes to the overall total pressure. So if we took a container and set the pressure at 100 kilopascals, we looked at the most simple reaction of A reactant changing into B, a product. Then at the very beginning, where there's no product formed, all the gas particles in our container are reactant molecules A. So we have 100% of our total pressure. So that 100% is designated by 1, meaning 100%, and then that's our total pressure. And it's this calculation of this fraction times by the total pressure that we call a partial pressure. As there are no particles or molecules of B, we're going to have 0, because 0% times 100 kilopascals. And so this calculation has come up with the partial pressure for the product B. So now we've got the partial pressure of B and the partial pressure of A, so we can work out Kp. So here we're obviously shifted very much so to the left-hand side, with this part of our fraction being very high. Now, during equilibrium, let's just for sake of argument say that we form 60% of B. Once we form 60% of B, that changes our percentage of B to A. And now we've got 60% here, 40% there. And so mathematically, we're using these percentages or fractions in order to do a weighting of the total pressure. We call this weighting the mole fraction. And the mole fraction is the number of moles of the species that you're looking at divided by the total number of moles altogether of all the reactants and products. So, for example, if you were told at equilibrium you had 1.2 moles of B and you had 0.8 moles of A, to work out the mole fraction for A, you would just take the moles of A divided by the total moles of everything. Now, in this example, we've only got A and B, so it's just 0.8 plus 1.2. And when you put that into the calculator, you will get 0.4 as the mole fraction. That's the first part of working out a partial pressure. The second part is timesing that by the total pressure. Okay, so let's have a look at these principles and how we would use it to work out Kp and its units by looking at a worked example. Okay, so I'm going to just give you a few moments to read through this question. So, when we're tackling this question, it's very similar to working out equilibrium quantities for a KC question. And we're going to borrow that ICE method, where we've got initial, change, and equilibrium, and then we've got two different rows here compared to equilibrium. If none of this makes sense, then go back and watch the video KC quantities at equilibrium, and then you'll see how that is different. So first of all, we want to fill out the initial table and the initial row of this table. So we're trying to find out the number of moles initially. So you can see here we had 10 moles of PCl5. So we're going to use that piece of data. And just like KC calculations, obviously no products are formed, so we can put 0 and 0 for both products initially. And then if we carry on reading and extracting the information, we want to now look at any equilibrium values that we're given. So it was heated to 500 Kelvin in a sealed vessel. At equilibrium, the pressure was 625 kilopascals and contained 6 moles of chlorine. So that's our piece of information there. I put that in on the row for number of moles at equilibrium, and it's for the Cl2. So that's all the information there in terms of moles initially in equilibrium. Our third step is to find our weigh in, and your weigh in is a column with both initial and equilibrium data. With this weigh in, you're going to work out the change that has happened from going initially to the equilibrium. Now, because this is a product and has changed, it's increased, it's going to be plus. This is a product, so it will also increase, and any reactants decrease as the reaction goes forward, as intuitive. So with this, we then start looking at the changes that also happen here, and we have to use the molar relationship just like we did in KC Year 2 questions. So in this example, because the stoichiometry or the molar ratios are 1 to 1 to 1, then the magnitude of the change here is going to be exactly the same as the magnitude of the change here. So this also increases by 6, and this would decrease by 6 because it's this 1 to 1 to 1 ratio. Obviously, say if this was a 3 to 1 to 1 ratio, you'd have to take this number and times it by 3. So this would be minus 18. So step 5 is then filling out the rest of this row with the information in the columns. So obviously we have 6 here, as initially it was 0, we're adding 6 onto that. And in this column here, we start with 10 moles, we take away 6, so we're left with 4 moles at equilibrium. Okay, so unlike KC calculations, where the next row would be to change the number of moles at equilibrium into concentration at equilibrium, we need 2 rows in order to work out the partial pressure of each of these chemicals that are in the overall system of reactants and products. So our 6th step is to work out the mole fraction. So obviously our equation is number of moles divided by total number of moles. So let's just work out the total number of moles, which is the sum of these 3. And then for each individual column now, we're just going to do the number of moles that appears in that column. So we're going to do 4 divided by 16. And then for both these columns, 6 divided by 16. With these mole fractions in hand, we're going to work out the partial pressure for each individual species. So we're going to do our mole fraction that we worked out in this row times by the total pressure. Now that is given in the question at 625 kilopascals. So here we're going to do 0.25 times 625, which gives us 156.25. And we repeat that same operation, but this time with the different mole fractions for the other species. And obviously these are the same because the mole fractions are the same. Now the 8th step is to use the expression for Kp for the particular equation that you're given. So here, because they're all molar ratios of 1 to 1 to 1, they're all to the power of 1 in terms of the expression. Remember not to use square brackets, they're curved brackets. And then with this expression of products over reactants, we just need to substitute in the values into these brackets and then come up with the answer for Kp. So we've got 352. Now in terms of the units, very similar approach to KC type questions. We just need to take into account the units of the different partial pressures. So this 9th step uses the information given in the question that we know the total pressure was in kilopascals. So these are our units of all our partial pressures. Then what we're doing is we're just cancelling out any terms that we can. So we know that it's 352 kilopascals as the units. So that's the method of coming up with the Kp for a reaction. Remember, you must be given some sort of pressure value for the total pressure in order to use this method. If you're not given pressure, then you're going to use the ICE method for KC questions instead. They often give you a temperature in here, and that is just a distractor, so just ignore it. It has no relevance to the question. Okay, so let's have a look at an exam question now. We've got 5 marker. I want you to pause the video here, use the same approach we've used previously to come up with a value for Kp. Okay, so first of all, you should be laying it out like so. And just at this point, if you did get this as the answer, then the method you've been using is spot on. If not, we're going to go through it step by step here. So our first bit is we're going to just extract the information from here. So you're told the chemist mixes together 0.45 moles of nitrogen with 0.45 moles of hydrogen. Obviously at the beginning, there's no moles of ammonia. The mixture is then heated and allowed to reach equilibrium. And then we're given some information. At equilibrium, the mixture contains 0.4 moles of nitrogen and the total pressure is 500 kilopascals. So we're going to use that later, but right now we're going to focus on this 0.4, and that was at equilibrium for nitrogen, so we're just going to put 0.400 here. We don't know any other information here, so this column is our way in. So you can see the change here is starting at 0.45, gone to 0.4, so we've decreased by 0.05 moles. Then what we need to do is use this change and the molar relationships to fill out these parts of this row. So nitrogen to hydrogen to ammonia is a 1 to 3 to 2 ratio. So to get from here to here, I would have to times this by 3. So I have to do the same operation to here. So I've got to do minus 0.05 times 3, which is minus 0.15. And then going from this column to this column, I have to times that by 2, so I'm going to times this by 2. Obviously this is a product, so it's increasing, hence the plus 0.10. Okay, so now we've got the information in order to fill out the equilibrium moles. So 0.45 minus the 0.15 is 0.3, and then we've increased to 0.10. So these are our moles. We need it in partial pressures, so we're going to use our mole fraction here. So that's the number of moles here divided by the total moles. So let's quickly work out those total moles. So the sum of 0.4 plus 0.3 plus 0.1 is 0.8. So our mole fraction is going to be here 0.4 divided by 0.8, 0.5. Here for this row, 0.3 divided by 0.8, which is 0.375. And then finally, we've got 0.1 divided by 0.8. Okay, now that we've got the mole fractions, we're going to focus our attention working out the actual partial pressure, which is the total pressure times these mole fractions we just worked out. So our total pressure was given here at 500 kilopascals. So we then times that by each of these mole fractions. Now we're going to have to get an expression for the equation that we're looking at. So we're going to do products over reactance, remembering the power is linked to the molar ratios given in the question. Then what we need to do is substitute in these partial pressures that we've calculated here into the brackets. Once you put that into the calculator and ensure that you don't make any mistakes in how you input that, you should get the value out of 2.37 times 10 to the minus 6. In terms of units, we just use the units of the total pressure and the partial pressures here. Then what we're going to do is just cancel those down. So we've got 2 on the top there, so we can remove this one, and then we can remove one of those. And then we just use the indices laws. If we flip this fraction, the power to the squared becomes minus 2 on the top row. And then that gives us our expression here. So this concludes our video on partial pressures and working out Kp. If you found it useful, ensure that you like it, and then make sure that you click on subscribe in order to get new videos as and when they're uploaded.